Welcome to the Explainer. Today, we're going to break down one of the most important pieces of technology in the entire world, the graphics processing unit, or as you know it, the GPU. Yeah, it started out just making our video games look pretty, but now it's the engine that's powering the whole AI revolution. Okay, so to really get this, let's start with a core idea. Think about your computer's main brain, the CPU. It's like a master chef, super fast, super precise, and it handles one really complex recipe at a time. A GPU, though, that's a different beast entirely. It's like a massive army of cooks on a giant assembly line. Now, they might not be as skilled as the master chef, but they can all chop thousands of onions at the exact same time in perfect sync. And that's the crucial point right there. A GPU's real power comes from its massively parallel design. What does that mean? It means it's built to do thousands of little jobs, or threads, all at the exact same time. And that ability, doing tons of simple things at once, is what makes it absolutely perfect, not just for drawing pixels on a screen, but for the huge repetitive calculations you need for science, and especially for artificial intelligence. All right, so to really understand how this thing works, let's peel back the layers. We're going to zoom in on the big picture, the macro architecture of a GPU chip, and see what really makes this super chip tick. You know, when you look at it, a GPU isn't just one single thing. It's more like a bustling city with all these specialized districts. You've got the main workhorses, the streaming multiprocessors, and we'll get to those in a second. Then you've got memory controllers acting like the city's logistics hub and interfaces to talk to the rest of the computer. And it's all connected by this super fast internal highway system. And this number, well, it's just mind-boggling. Modern GPUs can cram over 70 billion transistors, those tiny little on-off switches that are the foundation of all computing, into a space that's no bigger than a postage stamp. To put that into perspective, that's nearly 10 times the number of people on planet Earth, all packed onto your fingertip. It is a truly staggering feat of engineering. Now, all those billions of transistors need data, and they need it fast. So GPUs have this really clever memory pyramid. Right at the very top, you have these lightning-fast registers sitting right next to the processors. As you move down the pyramid, the memory gets bigger but a little bit slower, all the way down to this massive pool of VRAM. That's the big one. That's where you store things like giant, high-res game textures or even entire AI models. Okay, now for the really cool part. Let's dive even deeper. We're zooming into one of those districts we saw earlier, the real engine room of the GPU, the streaming multiprocessor, or SM. This is where all the magic really happens. So get this, each one of these SMs is basically its own powerful little computer. It's packed with hundreds of what we call CUDA cores. Those are the basic calculators doing the general math. But it also has these super specialized tensor cores built just for AI. And then you have warp schedulers that act like taskmasters, handing out all the jobs. And of course, it's all got its own super fast local memory to keep everything fed with data. So how in the world do you manage thousands upon thousands of these threads without it all just turning into chaos? Well, the GPU is smart. It groups them into these manageable little squads called warps. In NVIDIA's world, a warp is a group of 32 threads. And this is the perfect way to think about it. It's like a drill sergeant yelling "forward march," and the whole platoon of 32 soldiers steps forward at the exact same instant in perfect lockstep. That's a warp. It's just a beautifully efficient way to manage a huge parallel workload. And right there, inside the SM, that's where we find the secret sauce for the entire AI boom we're seeing today, the Tensor Core. This thing isn't a general-purpose calculator. Nope. It's a highly specialized circuit built to do just one thing with incredible speed, matrix multiplication. And as it turns out, that specific type of math, multiplying big grids of numbers together, is the fundamental building block of how neural networks learn and make predictions. And the impact? Well, it's absolutely staggering. Just look at this chart. It shows the performance on AI tasks with and without tensor cores. As you can see, it's not a small improvement. It's a massive, massive leap in speed. This is the innovation that lets us train these enormous AI models in just days, instead of years. So we've seen the blueprint, we've seen the architecture. But how in the world do you actually build something this impossibly complex? The journey from a grain of sand to an AI superchip, it's one of the most precise manufacturing processes humans have ever invented. This whole process is just breathtakingly precise, and it happens in some of the cleanest rooms on the entire planet. They use beams of light to etch these incredibly intricate circuit designs onto a wafer of pure silicon, one atomic layer at a time.
Then they implant ions to change the silicon's electrical properties. After all the layers are built up and tested, they literally take a diamond saw and dice the individual chips right out of the wafer. It's amazing.
But all of that amazing computational power comes at a cost, right? And that cost is energy. A lot of it. A single high-end GPU can pull down anywhere from 300 to 600 watts of electricity. That's as much as a microwave or even a small refrigerator, all generating a ton of heat in a very, very small space.
And that's exactly why thermal engineering is so critical. To keep the chip from literally melting itself, you need some really sophisticated cooling systems. This can be anything from those huge air coolers with heat pipes to complex liquid cooling loops that you'd find in a serious gaming PC or a massive data center.
So this brings up a huge problem, right? When you're packing billions and billions of these tiny components so close together, even one microscopic flaw can wreck the entire chip. So how do you keep making things faster and more powerful when you're already pushing up against the absolute limits of physics? Well, the answer is kind of brilliant and maybe a little counterintuitive. It turns out the way forward is to stop trying to build one single gigantic perfect chip. Instead, the future is all about building a team of smaller, specialized chips that all work together. And that brings us to the future, something called a chiplet architecture. Instead of trying to make one giant monolithic chip, which is super expensive and really hard to make without any flaws, you build a bunch of smaller chiplets. Here's the analogy. It's way easier to bake a dozen perfect little cookies than it is to bake one giant flawless cake. So you make these perfect little chiplets, and then you link them all together to build a processor that's even more powerful and way more reliable to produce. So you see, at the end of the day, designing one of these GPUs is this constant, incredible balancing act. Do you add more cores? Well, that makes the chip bigger and hotter. Do you want more memory bandwidth? Okay, but that's going to drive up the cost. It's this complex dance between performance, power, size, and the fundamental laws of physics and economics. I mean, just think about the journey. We went from a simple graphics card for playing video games to the foundational engine of modern artificial intelligence. The GPU is a true masterpiece of engineering, and its evolution has just been relentless. So that leaves us with one final, really exciting question. Now that we have all this unbelievable computational power at our fingertips, what once impossible problems are we finally going to solve next?